Class, I give you a quick review of pitch moment, and also the lift. The slope of the lift curve, CL alpha, is defined as partial CL over partial alpha, and this curve. Please notice that where the lift coefficient equals to 0, this point we call it. Let me put down. We call it alpha 0, right? So this is our lift coefficient. And under incompressible thin airfoil theory, we can write down CL alpha equals to 2 pi over radius. So for subsonic flow and including compressibility effects, we can have this theory of CL alpha equals to 2 pi over this. Later we can see that equals to a beta, which is a root of 1 minus Mach number square, and this factor is called the subsonic compressibility factor. Okay, at the subsonic speed below the critical Mach number, the lift curve slope can be written down as this. Okay, the above is the lift effective from the experiment, and we will use this later. Please do remember this formula. And now let us talk about a review of pitch moment. The aerodynamic center is located along the turbine, about which the moment is invariant with angle of attack, which means the partial cm over partial alpha at aerodynamic center equals to 0. And now let us consider the center of pressure. We call it a CP, and aerodynamic center we call it AC. So the lift generates on the AC. We have arrow here, and we would like to know what is the pitch moment generated on CP. And this is a very simple geometric problem. The moment at CP equals to which is M2 equals to M1 plus L. This is a lift times this distance xcp minus xca, and this bar means dimensionless because we have the lift here also dimensionless. So we can write down the moment coefficient, okay, like this. After very simple manipulation, we can have this, and then we derive it respect to CL. So we don't have this term, and we don't have a CL over here. So what we have is only left the distance between AC and CP. Okay, so another point is the moment coefficient at zero lift, also called CM0, is actually taken about the aerodynamic center. So we don't have the pitch moment at that point. So we will write down like this. And now we give a quick review of effects of flaps on subsonic airfoil section characteristics. And when the flap deflection, we all know that the lift will increase. So there are two effectiveness generated of a flap. The first one is the change in lift per unit flight deflection. It's defined as CL delta, and it's defined as partial delta CL partial alpha according to a constant angle of attack. For example, if we choose this blue line as angle of attack equals to 3 degrees, and we can see it clearly, this point is where the CL slope, the curve given by the zero flap. There is no flap deflection, and you can see this point is the lift coefficient given by the 20-degree flap deflection, which is greater than 0 degree. So this is a very good example to demonstrate that the flap can increase the lift. And the second change effect that is the change of the angle of attack per unit flap deflection. So this time we follow the green curve here, the green line here. We make the CL is a constant, and we can see that the alpha delta 0 greater than alpha delta 20 degree, which means we need more angle of attack to generate the same lift compared to larger flap deflection. Okay, this is another effectiveness of the flap. Okay, and here in our course, last time we mentioned that the plane flaps in subsonic flow, the section flap effectiveness can be estimated by this formula. It looks a little bit difficult, but the first term is, as I mentioned, is I should put down here, is a factor, and the second, the green part, is the ratio of experimental to theoretical flap effectiveness. As you can see, figure 5.15. Here is the necessary that we have, necessary information that we have to find what we need on these figures, and I will give you an example later. And the last term, the blue one, is effectiveness from thin airfoil theory, and you can see from figure 5.15 theoretical section lift effectiveness of plane flaps, and we can see the two. If we have the CF over C and T over C, then we can find the CL delta theory from this figure. Okay. In final, we have the relationship between the flap deflection and the pitch moment, and this is a formula. So if we have the longer flap or larger flap deflection, then we will have a stronger pitch moment, greater pitch moment. All right. So we have this on our last class, so I won't mention that too much. So let us see an example here. Aerodynamic characteristics of a subsonic airfoil with flap. Let us consider an NACA 2412 two-dimension airfoil with a chord line of 2 feet. The airfoil has trailing edge flap with a flap chord of 0.6 feet. Okay. If the airfoil section is at an angle of attack of 3 degrees, the flap is deflected to 20 degrees. All right, and the free stream velocity v is 600 feet per second. So please estimate the section lift and moment coefficient, right? CL and CN, right? And the location of the airfoil center. Okay. So other parameters that related to this airfoil to dimension can be obtained from the table. I didn't attach the table over here, but you can find that from your textbook. And this is all the necessary information that you have to solve this problem. And the first step, let us find out CL without having flap diffraction. Okay, so which equals to CL alpha times alpha minus alpha 0. Right, I mentioned that alpha 0 means the angle of attack without having lift, and this is a slope. Yeah, the concept is very easy. And then we can have this formula as we have seen in the above. We use the Mach number, which is 0.555 now, and this is CL alpha when the airfoil is stationary, which is 0.105. So we can obtain the CL alpha, which is 0.1257. Right. So for the left is we can have the alpha minus alpha 0, and the alpha 0 is minus 2 degrees, so we have the 5 degree here. So times them together, we get the 0.6286. The second step is to find the CL delta. The reason is that we need to check the figure to find out this term. Let me show you. We need to check this figure. We need to have this CL alpha over CL alpha theory and the CL delta over CL delta theory. Okay, we need to have this, so we need to find out this CL alpha over CL alpha theory. So this is what we do. So we need to do this. Okay, so the CL alpha equals to 0.105 given by the table over here. And this is the theory. We have to make it become the degree, so we just make the manipulation, and we will have the result as 0.958. So from the figure 514, we have this equals to 4.5, or let us see if it is correct. Wait, we have to find here. Okay, these two information, CF over C equals to 0.3 and T over C is 0.12. So let me enlarge this. So 0.3, and then we have calculated this as 0.96, so it's about roughly like over here, I guess. So it's about 0.98. 0.98 is roughly like somewhere like this at this point. So we have 0.98, and then we put it back to our formula. We can have the first term be calculated and the second term 0.98, and this we calculate here, we put it down. So we will finally have a zero consider the flap deflection. So we have 0.092 per degree. The third step is to combine them together. So this is the first term that we calculate over here, and we plus this because we need to times our flap deflection, so we times 20 here, 20 degree. All right, so this is our result. And the following step is to find out the cm in a similar way, and we have this from the table given by here. Okay, and what's left is much easier because all we have to do is follow this equation. Okay, so after that we can have this times 20 like here. So this is our second answer. And the final, the XAC, because the XAC bar is dimensionless, so we have to times C, the trend line, and the trend line is 2 feet, so we get the result of 0.494 feet after the leading edge. So this is an example that how to use information given by the question and how to find out from this table that you can see that on your textbook, and how to use these two figures as I mentioned in class, but I didn't show you how to do that. Now you can see how to do this. So please practice this by yourself and make sure that you're quite familiar with each steps. I see you next time. Bye bye.